hope everything's good with y'all. What we're going to do today is we're going to be talking about Isaac Newton, and we're going to be talking about how he figured out the universal law of gravity. Okay. Okay, the universal law of gravity is really, really important. We've used it to be able to study all the stars. We used it to figure out why the moon goes around the earth and why we go around the sun. And it really applies all through the universe. That's why it's called the universal law of gravity. Okay, now I sent you a video that I really hope that you watched, okay? Or if you didn't watch it yet, you can watch it later today. Okay, so did anybody watch that? Or not? Here, watch this. Let me let these other people in. Okay, so from your knowledge, where was Isaac Newton when he came up with the idea of gravity? He was under what?
An apple tree.
He was under an apple tree. That's the way it goes, yeah. Now what happened is he saw an apple fall, and when he saw this apple fall, what he thought about was, he thought, I wonder what makes the apple fall. And then this is the part you probably didn't know. He looked up at the moon, and he looked and he saw the moon, and he thought, I wonder if the same thing that is pulling the moon down is what is also pulling the apple down. Okay. All right, we're starting to get everybody. Still no Keisuke though. Phoebe's coming. All right, so what's really interesting, you guys, and Isaac Newton could figure this out, and I promise that you guys could also figure this out too. The Earth and the moon are a certain distance apart from each other. And it turns out that they are 60 Earth radii away. So, you know, one Earth radii is from the center of the Earth to the surface of the Earth is 6.371 times 10 to the 6 meters. And sure enough, the moon is exactly 60 of those away. Okay. And also, Isaac Newton figured this out, and you could figure it out too. Okay. When the moon is falling, it's falling towards the Earth, and the force or the acceleration rate it has is exactly 1/3600th of what the apple falls with on the Earth. Hey, okay, do you remember what the apples, you know, when stuff drops on the Earth? See, ready like this? All right, it goes down at 9.8 meters per second
squared.
There you go, 9.8 meters per second squared. Well, every single second, the moon also falls towards the Earth, okay? And it falls just a fraction of an inch towards the Earth every second. But the thing is, it's going sideways. Isaac Newton calculated that and then realized that must be somewhere involved in this universal law of gravity, okay? Now, you guys, I sent you two sheets, okay? I sent you a sheet that has notes and a sheet that has an assignment on it, okay? So could you open up the one that says notes real quick? And then what I'd love you to do is to split screen it so that what you're doing is you're looking at half of this screen, what I'm going to show you, and half of the notes where you can write on the notes. Okay? All right. If you're worried about it, I'm going to send all the right answers, the filled out thing to you. Okay? So if you want to just look along, that would also be fine too. All right. My first class, if you can look at the remains of all this, my first class did not go well. It did not go well at all. It was because we had so many computer problems. Okay, here we go. All right, look at this right here. This is Newton's universal law of gravity. Oh, you know what? I didn't share my screen with you. I'm sorry. Let me share my screen with you so you can see what I'm talking about. All right, this is Newton's universal law of gravity, okay? And F stands for the force of attraction between any two objects. Somebody else is trying to get in the classroom. Here we go, Christina and Carter. There we go. All right, so any two objects in the whole universe are attracted to each other, okay? If I put Bao and Derek in outer space, they would start to be pulled together really slowly. And they might even start orbiting each other, okay? like this, really, really, really slowly. Any two masses in the whole universe are attracted to each other, okay? And it goes like this. The force is the attraction. G is this thing that's called the universal gravitational constant. It seems to apply everywhere in the universe except if you get really close to black holes. M1 and M2 are any two masses, like Dirac and Bow, okay? And then when you say divided by r squared, that's the distance between the two of them squared. And this is where Isaac Newton looked at the moon and the earth, and he figured out how far the moon was. And he was able to figure out that it must have something to do with something. This is called the inverse square law. And that's what the 1 over r squared is. All right, so let's use this as an example. Let me show you just basically how you can use this equation. Like I said, we were working on this some in our first class. Okay, so let's say, there's the answer actually there. Let's say that Dirac and Bow are out in outer space, okay? So here they are. They're out in outer space. And let's say that they are 1 meter apart, okay? Let's say that both of them have a mass of 50 kilograms. All right? So there is going to be a force of attraction between both of them. They're going to be pulled towards each other. You can use this equation, F equals G M1 M2 over R squared to figure this out. So it's really, remember what I told you about physics? It's when you learn about the equations, you can just plug numbers in and you can figure stuff out. So G is this universal gravitational constant. It's a really small number because actually gravity is pretty weak, 6.67 times 10 to the negative 11th. Remember how we talked about that electromagnetism is way stronger than gravity? That number right there, the 6.67 times 10 to the negative 11th, right there, that helps gravity. It makes gravity pretty weak. It shows how weak it is. The 50 times 50, that's M1 times M2. That's the mass of the two boys. Now they're separated by 1 meter, but you got to square that. Now what I see 8th graders forgetting to do, 8th graders forget to square, they forget to square that distance a lot. All right, so now when you plug all those numbers in your calculator, all right, you come up with this, 1.67 times 10 to the negative 7th newtons. Now that's not very much, but you know what the thing is? Dirac and Bow don't have very much mass, all right? But if you were talking about two planets, there would be a huge amount of force, okay? Now let's go on here. What if I said that you could figure out how massive the Earth is just by jumping off a chair? So if I said, Sia, I want you to climb up on a chair and I want you to jump as high as you can and fall down to the floor. Did you know we could just use just that to figure out the mass of the Earth? Somebody had to figure out the mass of the Earth, you know? And so they used Isaac Newton's equation to do this. All right, now watch. If this is Sia right here, and she's jumping off of her chair, isn't she going to go down at 9.8 meters per second squared? And isn't the force of gravity, what you guys call the force of gravity, going to pull her down? Now, I've always been telling you the force of gravity or the force of weight is FW equals mg, right? That's just plugged in your head, right? Hey, Sam, could you pull that off of your face, please? That's distracting me. All right, so watch this. So that means the force is the same thing as the force of weight. That's like how hard Sia is being pulled down by the Earth. And then we would go G, the mass 1, which is Sia, and mass 2, which is the Earth, divided by how far apart they are. Now, you guys, the force of weight, FW equals mg, right? So we're going to go m1g. That's the mass. See how I'm substituting in? That's the mass of Sia times 9.8. All right. And then right here, we're going to go G, M1, M2 divided by R squared. I'm sorry if it's running together a little bit. Let me see if I can clean that up a little bit right there. Okay. Does anybody notice that there's an M1 on both sides of this? If there is an M1 on both sides of that, what can I do, everybody?
Cancel out.
Cancel
Thank
them
you.
out.
Yeah, see this, look, I can divide through by M1 and all of a sudden it's gone. So look, now this is G, that's 9.8. Okay, this is going to be equal to big G, which is 6.67 times 10 to the negative 11th, times the mass of the Earth, which I supposedly don't know, divided by the radius of the Earth squared. And even the ancient Greeks knew the radius of the Earth. Okay, 2,000 years ago, they knew this. So do you see I know every single thing in there except for the mass of the Earth? Now watch, I'm going to solve for M2. So how would I get the R squared to the other side? Would I divide or multiply, everybody?
Multiply.
Yeah, so I got G R squared equals big G times the mass 2, which is the mass of the Earth. Okay, I want to get mass 2 by itself. So what do I do now? Do I multiply or divide, everybody?
Divide it.
Yeah, you're going to divide. So watch this. G, which is 9.8, times the radius of the Earth squared, divided by big G, is equal to the mass of the Earth. Okay, so let's plug these numbers in. So we got 9.8. That's how fast you fall. I know there's a bunch of numbers here. I'm sorry if this is freaking you out. It doesn't need to. It's not hard. And then right up here, the radius of the Earth is 6.371 times 10 to the 6th. But you've got to square that. And then you divide that by the universal gravitational constant. 6.67 times 10 to the negative 11th. And this is equal to the mass of the Earth. Okay, now let me do the calculation real quick. You can too if you want to back me up. Be 9.8 times 6.371 times 10 to the 6th squared divided by 6.67 times 10 to the negative 11th. And there it is, 5.96 times 10 to the 24th kilograms. So M2 is 5.96 E24 kilograms. That is how we know the mass of the Earth. From Sia just jumping off her chair. But it could have been Derek, or it could have been me, or it could have been Sam. Because see, look, the masses, Sia canceled off. It didn't matter who jumped off the chair. All right? All right, now, a real important piece of information. Watch this. What is the force between the Earth and the sun? Okay? So there's some important details we're going to have to throw at you right here, okay? That's going to be important for your assignment. Okay, watch this. The force between the Earth and the sun. Let's just fill in these numbers. G is 6.67 times 10 negative 11th. The mass of the Earth now. Now, usually I say it's 5.98 instead of 5.96. So we're going to do that. 5.98 E24. And then right here, the mass of the sun is 2 times 10 to the 30th. Okay? The distance between the sun and the Earth is 1.5 times 10 to the 11th meters and squared. See, so we can figure out all this stuff right here. Here's the data I was giving you right over there on the right side. When we just multiply these together, you guys, then we can figure out exactly how hard the sun is pulling on the Earth. Okay, now right after this, I'm going to explain your assignment, okay? So 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th times 2 times 10 to the 30th divided by 1.5 times 10 to the 11th squared. Okay, so if I did all that math right, let me check my numbers. It looks like it's all correct. Okay, so the force between the Earth and the sun is 3.54 E 22 newtons. So this is the force that's causing the Earth to go around the sun. Okay? All right. Let me unshare for a second. All right. I just threw a bunch of numbers at you. Okay? But guys, look at this. It's an equation. So all you have to do is just write the equation down and fill in the numbers and solve for it. Can we all do that? It's just simple algebra. Okay? All right, now I'm going to show you what your assignment is. This assignment is supposed to be due tomorrow. Okay, so could you open that thing up right now? It's the one that says Newton's universal law of gravitation, and it's got a big table on the front. Okay, now I'm going to open it up too so that I can help you. Now, let me see. We started class at what time? At 10? Yeah, so we still have 13 minutes. Okay. All right, so here we go. Let's share the screen real quick so I can help you guys. All right, okay, this is what I want right here. Now there's some special things about this, okay? Okay, here is the law you have to use. Here's like right there, that's what G is. And it explains what the other things are. Now, what we're gonna have to do though is we're going to have to find right here, it says, the mass of the sun is 2 times 10 to the 30th kilogram. Use this and the data above to find the force of gravity between all of these objects. Okay, so I'm going to show you how to do this right now, okay? Oh, Keisuke got here.
E.
Keisuke, I'm sorry you're having so much trouble.
Good job.
Okay, so ready, do this. Everybody write down the equation. Okay, and now what we're going to do is we're just going to fill in the equation. How hard is the sun pulling on Mercury? Okay, so you're going to go like this. F equals, okay, G. What's G, everybody? 6, it's big G. 6 point, come on, help me. 6 point what? 6.67 times 10 to the negative 11. There you go. All right, now I'm about to tell you something really important, so really hang on to this. Okay, so between the sun, what's the mass of the sun, everybody? .0 times what?
10 to the 30th.
There you go. So it's 2.0 times 10. Remember the E means times 10 to the 30th kilograms. Okay, now we got to figure out the mass of Mercury. Okay, so now let's analyze this table. Here's Mercury. Okay, now Mercury evidently has a mass of 0.330 times 10 to the 24th. Okay, so 0.330 times 10 to the 24th. Do you see how we're just filling out the table? Okay, now what goes on the bottom, everybody? What is this? This thing right there, what is that? That R, what is that R?
The universal.
No, not the universal.
Radius.
Distance between.
Yeah, Isaac Newton said it was the radius at first. It's the distance between the two masses. Okay, so see this, look right here. The distance from the sun, because what we're talking about is the force between the sun and Mercury. Now, we got a problem though. Look at this right here. The kilometers, do you see this? That's not the right unit. It's supposed to be in meters. So instead of 10 to the 9th or 10 to the 6th, you're going to have to write 10 to the 9th meters, okay? You with me on that? Okay, now look right here. It says right here that Mercury is 57.9 times 10 to the 9th meters. Now we got to square that. All right, so now all you have to do is calculate it. So you're going to take 6.67 times 10 to the negative 11th times 2 times 10 to the 30th times 0.330 times 10 to the 24th. And you're going to divide it by 57.9 times 10 to the 9th squared. Okay? This is using Isaac Newton's law of gravity. Now, hey, you know what I'm going to do? What I'm going to do is I'll calculate it, and then I'll see if I get it, and if you get it the same answer, then it must be right. So everybody start calculating. Want to hear those buttons going. Okay. Anybody brave enough to share an answer?
(1.131314E22).
Okay. I think that's right. I got 1.31. Did you say 1.3 or 1.13?
Or 1.31314.
Yeah. Good. Excellent, Derek. So here's the answer. 1.3 E 20. Was it 22, Derek? Is
Yeah.
that right? Good. There you go. There's your answer. All right. So now this is your homework to fill this thing out. Okay. So there is 4 more. How hard is the sun pulling on Jupiter? How hard is the sun pulling on Saturn? How hard is there 5 more or 4 more? 1, 2, 3, 4. I guess there's 4 more. So we're going to be talking about outer space pretty soon, which is pretty cool. We have to understand about gravity, though, to do that, okay? And that's why we're doing this. So it's just basically using this equation and plugging those numbers in. Okay, so I'm going to let you guys, if you want to keep working on this and then say, hey, what everybody get on the second one? What everybody get on the third one? I'm cool with that.
Mr. Hawley,
Yeah.
can you reteach what you had just said? Because I couldn't get into the Zoom meeting and
Case, I still can't even see you. Can you, is your camera on? There you are.
so
Why were you having so much trouble getting in? I know we were all having trouble, but
I re-entered the code again and again, but it wouldn't work. And then it finally worked on like the 100th try.
that is weird. I'm sorry you're having a big pain. Hey, Bao, I can't see you either. Can I see you, please?
Sure.
There he is. All right. Hey, while I've got everybody's ear, there's several of you guys that have zeros in your grade book. Could you take care of those? Some of you have videos that I still need to look at, and I'll try to look at those this evening. Okay. All right, KSK, ready?
Just a second.
Okay.
Yeah, I'm ready.
Okay. Hey, the rest of you, if you want to share answers, I'm cool with that. The chat is off, but when I pause with KSK, then you guys can say what everybody get for this. Okay. So KSK, this is about Newton's universal law of gravity. So it's F, which is the force, equals a big G, which is a constant, okay, times one mass times another mass divided by the square of the distance between them, okay? And the distance has to be in meters. All right, so did you do that first problem with me?
Yeah, I did, but I don't really understand it.
Okay, let's look at the second problem instead, okay? And then if you want to, you can go back and look at the movie and you can look at the notes as we did the notes, okay? All right, hey, so everybody, I'm gonna look at the second problem as well. Okay, so what did everybody get? Did anybody get an answer? Nobody wants to say?
Are we
Okay,
always gonna times it by
10 to the 9th.
Yeah, because that's how that table's set up. Basically, it's comparing all the distances in the same kind of powers. That's why. All right, case K, do this. All right, so on the second one where it says force between the sun and Jupiter. So case K, write down F equals G M1 M2 divided by R squared. Okay? And then what I want you to do is I want you to write, just like you did on the example above, write 6.67 times 10 to the negative 11th. That's G. And then M1, we're always going to use the sun. So that's 2.0 times 10 to the 30th. Okay. Now you're going to have to multiply it times the mass of Jupiter. Okay, so KSK, look on that thing and figure out what the mass of Jupiter is.
Wait, where
It's
do you get G? 1,000?
G is at the very top. It's a universal gravitational constant.
So
At the very top.
yeah.
Okay, so now, hey, everybody, KSK. All right,
1,000.
Jupiter, tell me the mass.
1,898.
Times.
10 to the 24th.
Excellent, good. So that's on top. Now on the bottom, KSK, goes the distance between the sun and Jupiter, okay? So look all the way at the bottom of that table.
So it'd be 700. Wait, 770.
Yeah, 778.6
times 10 to the 6th.
times 10 to the 9th, because we got to make it into, it's shown in kilometers. We need it to be in meters, okay? All right?
How do we convert it from kilometers to meters?
Instead of going 10 to the 6th, just say 10 to the 9th, and that does it,
Okay.
okay? Now don't forget to square it,
Okay.
all right?
And then I just calculate from there.
There you go. Then you just calculate it.
Okay.
That's all you
Did
do.
everybody get an answer?
Yeah, hey, what'd everybody get? I'm going to call out Kaylee Villagomez. Did you do the second one?
I'm not done yet. I'm calculating right now.
Okay, let me see. Phoebe, did you calculate the second one yet?
I'm still calculating.
You guys. Are you guys scared to say your answer?
No, I'm not. I'm actually
not scared.
working on it.
Hold on, I'll say
Now,
it.
did you get it yet?
Hold on, I'll say it in like 0.5 seconds.
0.5. Go.
Okay. Oh yikes! I don't even know if that's right. I got 4.1766 10 to the negative 28.
Okay, it's probably not going to be negative 28 because, that would be like a force that's less than 1 Newton.
I got E23.
What'd you get?
I got the same numbers, but instead of 10, whatever, I got E23.
That sounds more logical.
It's negative though.
Yeah, it's not going to be negative because of the fact that the force between the sun and Jupiter is going to be large. Okay. All right. Anyway, I'm going to let you guys work on this. If you want to come back and see me at tutorial time, I can give you some help. Okay. Remember, tutorial time is at what time today?
11:55.
Yeah. Good. I'm sorry, in case, I'm sorry you had trouble getting into class. I'll record this. I'll turn it into a movie if you want to watch it, okay? All right. So I'll see you guys later. Bye-bye.
See you later. Bye.
See you later. Bye.